you, Roger. So I'd like to just start with a very brief history of the lattice clock program at NIST. It all started over a decade ago when Chad Hoyt, Zeb Barber, Chris Oates, and others built up the very first terbium lattice clock, with key components being the lattice-trapped atoms, of course, and then the cavity-stabilized laser that talks to those atoms. Now, shortly after it became operational, it made several important contributions to the field of lattice clocks. But as this clock improved over that time, it really became essential to have a second clock to really assess the performance. So a few years ago, our group completed construction of YB2, our second ytterbium lattice clock. One of the first things we did then was run the clocks against each other to test the stability. And what we got was an Allen deviation here that averages down as white frequency noise at a rate of 3.2 times 10 to the negative 16 per tau, ultimately getting down to this 1.6 times 10 to the negative 18 level. And I should mention that tau is the averaging time in seconds. All right, this purplish band that you see here represents our best estimate of two important noise sources that affect the stability of our clock. The first one being quantum projection noise, related to the quantum nature of the atoms and how many that we're interrogating. And then the second is the Dicke effect, which I want to spend a little more time talking about. So if we go back to the case of a single lattice clock here, well, our clock operates on a cycle where only a fraction of the cycle are we actually talking to the atoms with the clock laser. And then we have this intervening dead time dedicated to the cooling, trapping, state preparation, and detection. And it's this periodic interrogation of the atoms that has the effect of downsampling high-frequency laser noise, really making it look like a more problematic low-frequency noise. It's really the essence of the Dicke effect. All right, so when we built up YB2, our second clock system, well, we built up a whole other atomic system. We let that atomic system share the clock laser with the first system. And in this arrangement, there's really a couple of ways to interrogate the atoms. On one hand, we can do a synchronous interrogation, where we line up the timing sequences here. Now, in this case, both clocks are subject to the Dicke effect, but in the comparison, this happens in a common mode fashion, so it actually gets rejected from the comparison data. All right, well, if we're trying to assess the performance of a single clock, either YB1 here on its own or YB2 on its own, it's really unfair to throw away this really important noise source. So instead, we do an asynchronous interrogation that looks like this. Now, both clocks are susceptible to the Dicke effect, and the comparison data is as well. And this is how we got the results I showed you a few slides back. So while we're happy with these results from a few years ago, of course, we want to make things better, and so we've made some upgrades to our system, most notably to the cavity-stabilized clock laser. So we now use a subharmonic of the clock frequency, which has lower losses in the cavity mirrors here. We've also improved the thermal and acoustic isolation from the environment. So with this effort, we then get a better laser, which automatically means less stick noise. However, there's additional benefits that come along with this. Because we have a better laser, we can interrogate our atoms for a longer period of time. This, in turn, implies higher duty cycles, whereas we've traditionally been limited to the level of about 30%. We can now operate at duty cycles of 50% or greater. And traditionally, we've used Rabi spectroscopy in our work, but this longer interrogation time now really makes Ramsey spectroscopy more appealing to us. All right, so with these upgrades to our clock laser, as well as some other upgrades to our system that I won't delve into, it's now time to reassess the stability of our clocks. So again, we use asynchronous interrogation. We use a 50% duty cycle here with the Ramsey spectroscopy, so our timing sequence looks like this. And when we do our comparison, we get a result 1.5 times 10 to the negative 16 per tau. So this represents just over a factor of 2 improvement in this coefficient, the stability at 1 second if you extrapolate the line back. All right, well, we're happy with this result, but there's actually more to be said here. This isn't really the primary result we were going for, because if we look at the timing sequence, we see that at any given time, the clock laser is talking to some set of atoms, whether it's in YB1 or YB2. And it turns out that because of this, we can essentially draw a line around our whole system here that includes both atomic systems as well as the clock laser. We can just call this a single composite clock with 0 dead time. This idea was first put forth by Dicke, for whom the Dicke effect is named after. And now that we have this single composite clock, of course we want to know what's the stability of this. Well, a real rigorous evaluation would involve building up a whole nother composite 0 dead time clock. Okay? 2 atomic systems, another clock laser. All right, needless to say that this isn't going to happen in the immediate future. All right, so let's go back to something that we can measure, YB1 versus YB2. Let's consider these 2 different interrogation schemes that I talked about, asynchronous interrogation and synchronous interrogation. We can make a table here that includes all the different noise sources that affect the comparison in both cases. This includes quantum projection noise, photon shot noise, et cetera, et cetera. And what we find is that we have all of these noise sources in each case. They affect the interrogation either way we do it. The one exception is the Dick effect. Like I said, for synchronous interrogation, it gets common mode rejected. Well, it turns out that this right-hand column here is very representative of all the noise sources that we expect for this composite zero dead time clock. So what that really means is that if we keep all our interrogation parameters here the same, notably this 50% duty cycle, but just replace the asynchronous interrogation with synchronous interrogation, now this can give us a good measure of the stability of our composite zero dead time clock. So when we do this measurement, we get a result 7 times 10 to the negative 17 per riptile, which is yet just another factor of 2 or just a little bit more from the previous result that I showed you. However, this isn't the whole story, because in our measurement here, we're actually interjecting additional dead time in this comparison that isn't there for this interleaved composite zero dead time scheme. So we argue that it's actually fair to scale this time axis down by a factor of 2, which really corresponds to dividing this coefficient by a factor of root 2. So really what I'm claiming here is that this composite zero dead time clock really has a stability of about 5 times 10 to the negative 17 per riptile. So now we're talking about having a single clock system here that's capable of averaging to 1 times 10 to the negative 17 on just the order of half a minute. And it's 1.6 times 10 to the negative 18 level that we got to before by averaging for several hours. Well, in principle, this thing can do it in the order of about 20 minutes. And since these comparisons are pretty quick measurements for us, we just went ahead and did it a number of times, and we're able to reproduce this result quite well over and over again. All right, so this is really where our clock stands in terms of stability. Now we also want to improve the accuracy of our clock. So I'm going to shift gears a little bit and talk about lattice light shifts, which historically have been one of the leading uncertainties in our clock. And this is something we heard a little bit about in the last talk, but I'll just for completeness sake, I'll give a quick review again. So we have our optical lattice here, and this lattice provides a potential for our 2 clock states, a singlet F0, triplet P0. And to first approximation, this potential can be written in terms of the intensity of this lattice, the polarizabilities of the respective states, and then the spatial factor here that just corresponds to the intensity profile within this lattice. It's just a standing wave. Well, the real major insight that paved the way for these lattice clocks was to note the wavelength dependence of the polarizability here and exploit this to tune the polarizabilities to be identical for the 2 clock states. So in this case, the potentials are independent of clock state. These motional energies here are independent of the clock state. And when you drive this transition, and regardless of what motional state we start in, all these transitions are going to look identical. Moreover, they're all going to look like the atomic transition frequency. So what we end up with is some narrow spectral feature that's centered on the atomic transition frequency. All right, so for the most part, that works great. However, as we push down to the 10 to the negative 18 levels, there's a couple other things we have to think about. Collectively, I call these non-magic effects. So this includes detuning from the magic wavelength, which will be there to some degree whether we want it or not. There's also magnetic dipole and electric quadrupole coupling with the lattice field here. And then there's also hyperpolarizability, which is the next highest order electric dipole interaction, 4th order in the electric field. So when we consider these effects here, well, we have to add a few more terms to our potential. That means that our potentials are going to look a little bit different than they did before, and these emotional energy levels are also going to look a little bit different. And when we drive this transition, no longer can we expect these transitions to all look identical to one another, nor can we expect them to be equal to the atomic transition frequency. So what we end up with then is some spectral line that's shifted from the atomic transition frequency. It's pretty clear to see from the expression of the potential here that this clock shift is going to depend on both the intensity and the wavelength of the lattice laser. However, it's also important to note that because these transitions look a little bit different from one another, that the clock shift is also going to depend on the emotional state populations that we start with down here. This is an important point that I think gets kind of brushed over a little too quickly in the literature sometimes. So in general, we'll have a frequency shift in our clock due to this. We're okay with having a shift in our clock as long as we know what it is. So to assess the shift, we use a basic strategy where we just measure the frequency shift versus intensity for a number of different intensities, and then we just extrapolate down to 0. All right, to help us with this, we've made a buildup cavity that allows for 100 times power enhancement within this lattice to get depths on the order of about 2,000 recoil. So at the end of the day, we're not necessarily interested in working with such deep lattices, but this gives us a really large lever arm to assess the shift for our normal conditions, which is about 100 recoil. So I want to come back to this slide in just a minute. However, I want to show some quick experimental data in the meantime. So at each intensity or depth that we work with, we do a quick trace of the sideband spectrum. The reason we do this is because this gives us information about the atomic temperature. And when we do this, we see a very interesting behavior. We find that the temperature scales linearly with the intensity. This isn't something that we expected going in, but we suspect that's due to stark shifts on the cooling transitions. So as we increase the intensity, we're essentially inhibiting the cooling and ending up with higher temperatures. In any case, it's a clear behavior that we see here. All right, and we'll see a little bit of that in just a few minutes. But getting back to this slide, like I said, we want to measure the frequency shift versus intensity and extrapolate to 0. Well, we have to ask ourselves a very important question here, and that's what is the functional form of this extrapolation that we need to use? On one hand, we can do a linear fit to this data, and we'll get one result for the intercept here. Or we can do some higher order fit. There's even suggestions there should be intensity of the 1/2 and 3/2 terms. All right, well, in any case, this is going to require some theory. There's a couple of ways of looking at this problem. The way I like to look at it is, let's just start with the magic conditions, where the potential is independent of the clock state, the motional energies are independent of the clock state. Not only that, we also have these wave functions that are independent of the clock state as well. And let's just call that our 0th order condition. And all these non-magic effects that I talked about earlier, well, those are really small by comparison, so we can just take those as perturbation. And the reason I like this view is because it's really straightforward then to go from an expression for the potential that we had before to an expression for the clock shift. Really all we have to do is replace the atomic factors here with some differential value evaluated between the two clock states. And then this spatial average, or spatial factor, we just replace with some average value. It involves an expectation value over these wave functions, followed by a thermal averaging over the populations here. So the wave functions depend on the depth of the lattice or the intensity, and the populations depend on the temperature. So generally, these spatial averages here depend on both the intensity and the temperature in some way. Now we know this, potential here looks like. It's just a cosine squared function. So it turns out then that we know what these wave functions look like. They're just these analytic mapping functions. So this means that it's very straightforward then to evaluate these spatial averages here for really any range of intensities and temperatures that we might be interested in. As an example, let's consider the factor of sine squared kz. When we do the evaluation, we get something that looks like this. Now we can say a couple things right away. If we go down to the bottom right-hand corner here, well, this corresponds to deeper lattices with colder atomic samples. In this case, we expect the atoms to be more localized, and that would correspond to smaller values of sine squared kz. And indeed, that's what we see with the purple color being colder, or smaller values, I should say. And then going in the opposite direction, well, this corresponds to shallow and warmer. We expect the exact opposite, and that's what we see up there too. But what's of more concern to us are these straight lines that branch out from the origin, because these correspond to cases where the temperature is proportional to the intensity. Like I said, that's what we observe in the lab. And what's interesting about these lines then is if we walk along these lines, we see that this value of sine squared essentially stays constant. So almost by pure accident, we've just landed upon the contours of this plot. Likewise, we can do a similar analysis for these other spatial averages, cosine squared, cosine to the 4th. And we see that those are largely constant. And the first one here is just a gimme because sine squared plus cosine squared has to equal 1, but we do see a similar result for cosine to the 4th. All right, now what all this implies is if we go back to our expression for the clock shift, where we have these spatial averages here that in general depend on the intensity and the temperature, well, we can just replace those with constants. And then the rest of this expression here just collapses down to a very simple form where we have one term that's linear in intensity and another term that's quadratic in intensity. And then we have these two coefficients here that generally depend on wavelength. Okay, so now that we have our very simple functional form, we can go ahead and look at our experimental results. Like I said, we want to measure where we did measure the clock shift versus intensity. Now, the different colors that you see in this plot just correspond to different choices of the wavelength. And for each wavelength, then we fit the data to this functional form, neglecting the offset because that's just an artifact of the way we do the measurement. And so when we do the fit, then we extract these coefficients A and B. And we can go ahead and we can look at how these coefficients vary with the wavelength or lattice frequency as the case is in this plot. But the point is that after taking all this experimental data, we have a good characterization of these coefficients A and B. We can throw a little bit of theory at this and get information about these atomic factors down here that are kind of wrapped into A and B, as well as the magic wavelength if we want. However, that's not really what's of concern to us for clock operation, because really at the end of the day, we're just going to pick whatever wavelength is the most convenient for us for our operational conditions. So suppose we want to operate at a depth of 110 recoil, which is pretty standard for us. Well, then we're just going to pick a wavelength from this group or somewhere in between that gives a nice quadratic minimum at 110 recoil. And then with our very simple functional form together with these coefficients that we evaluated experimentally, we can evaluate what the clock shift is. In this case, we get -4 plus or minus 1 times 10 to the -18. And this is really the main message here, is that we've evaluated these clock shifts now at the 1 times 10 to the -18. This includes all the electric dipole, magnetic dipole, electric quadrupole, or magnetic hyperpolarizability, all these different effects, right? They're all wrapped into this. And moreover, we're very insensitive to whatever the intensity is. So we don't really have to know the intensity all that well because we're sitting at this flat point here. So even a 50% fluctuation in the intensity only corresponds to a 1 times 10 to the -18 shift in the clock. And we can do much better control than that. So this is really the final results for the lattice light shifts. And just as my final slide, I wanted to put up a quick table here of the 2009 published uncertainty for the YB clock and compare it to where we think we are today. You can see that a number of these really big numbers here have been knocked down significantly, including the lattice light shifts that I just talked about, as well as some of these smaller numbers, and we still have a few blank spots there, but we hope to complete this in the next several months. With that, thank you for your attention.